average case harness that Tselil has the best title ever in the entire workshop.
Yeah.
And I am as eager as you to find out what she has to tell us.
Okay, yeah, thanks. Actually, the title that I have on the schedule is something about new average case hard problems ? Yeah, I was teaching a new undergrad class in the spring, so when the email came to me asking what I would talk about, I just wrote that down, and then I skipped the email that asked me to update the title. So this is what you get when you ignore your email inbox. But really, what I wanted to do is a tutorial about the low degree method. Have you guys heard of the low degree method? Raise your hand if you have heard about it. Raise your hand if you know what it means, like confidently. Okay, that's pretty good. I like this. Okay, so it's going to be a tutorial, and I plan to make it really basic. Please ask as many questions as you would like. And I know that I'm opening myself up to fire when I say that, but I really, really want it to be accessible. Okay, so what is the low degree method? So the low degree method is basically this is a way to check if a hypothesis testing problem resists a specific set of attacks. Okay, I'll write even a canonical set of attacks. Okay, and it turns out that for many problems, which are natural hypothesis testing problems that come from the learning and statistical inference style questions, when the problem resists this specific set of canonical attacks, that coincides with the threshold at which we don't know any algorithms that will attack it at all. Okay, so this is also like in another thing to say is that with this low degree method, I feel like I have an endless supply of problems that appear to be hard on average. Okay, now, like with anything, just because we know that the problem resists a canonical set of attacks doesn't mean that tomorrow someone couldn't come and produce a new attack that would actually show that the problems are easy. So I would say that the right thing to do is to think about this as a heuristic, right? Like, I'll teach you the low degree method. You'll know the low degree method. You try to design a new problem which seems hard on average. It could be pretty different than anything that you've seen before, and still you'd be able to check if this canonical set of attacks will attack or not attack your problem. But you should still be skeptical, of course, that there could be some other attack that's not inside this class. But at least for this canonical set of attacks, we're going to provably resist them. Okay, so the plan, if I write, how low can you guys see if I write like this? People in the back? Okay. Even lower? Okay, let's say that this is as low as I'm going to go. Okay, so my plan is first I'm going to explain the setup, which is basically the style of problem is going to be a null versus planted hypothesis testing problem. Okay, then I'll describe a specific model of computation, which is just going to be like evaluation of low-degree polynomials. Okay, this is like, you guys are like, well, okay, I already know what your model of computation is, but there's like one or two technical caveats that I'm going to have to add. Okay, then I'll explain what the low-degree heuristic is. /method. And then finally, I will speculate. Well, I'll tell you about applications of the low-degree method in crypto so far. At least I will list applications so far, and I'll speculate about whether one can get more. Okay, so crypto. All right, so yeah, and as I said, feel free to interrupt me anytime. Okay, so our model of computation, or our setup, is that we're going to be trying to solve hypothesis testing problems. And the type of hypothesis testing problems that we're going to solve are that on the one hand, there's some distribution Q. This is going to be a null distribution. Think about it as a distribution over Rn. And often it will be nice if this is also a product distribution. Though technically what I'm saying does not require it to be a product distribution. Okay, so this is a null distribution. And I also have a planted distribution. Also over Rn. Okay, and my goal is I'm given some sample x, which is sampled with probability half from Q and with probability half from P. So with probability half, I sample from the null distribution, totally unstructured x. With probability half, I sample from P, the planted distribution. There should be some kind of planted structure here. And my goal is given x to determine if x is from P or Q with probability, let's say, strictly better than half plus epsilon. Let's think about epsilon as being a constant, though of course you can tune these parameters however you want. Okay, so let me, I think it's easiest to explain this with some examples. So let me just list a couple of examples. So maybe like the simplest canonical example is the planted clique problem. Okay, here I think of x, so the null distribution Q. I want this to be an Erdős-Rényi graph with edge probability half. So this is just G and half. I can just think about this. This is equivalent to sampling every edge in or out with probability half. So this is the same as like Bernoulli half tensored n choose 2 times, where n is like the number of vertices in my graph. Okay, so I'm in this situation where I have a null distribution, which is a product distribution over R capital N, where I let capital N be n choose 2. And then my planted distribution P is just that I sample G n half, but then I add a K clique on a random subset of vertices. Okay, so here I have this planted structure, and I can be given the description of the graph X. This is like the adjacency matrix of the graph. I don't know where the clique is. Okay, so there's some planted structure, and these two distributions are different whenever k exceeds 2 log n. Now, when k is really large, this problem is easy to solve. You can do stuff like degree counting and figure it out. But when k, I'm getting near the bottom of where I'm allowed to. But when k is less than root n, but bigger than 2 log n, the problem appears to be hard. Meaning, like, many people who are very smart tried to solve it, and we don't know how yet.
Well, it's true also when k is small. So when k is small, you don't care. It's not interesting.
Yeah, when k is less than 2 log n, these are actually the same. These distributions are close in statistical distance. So you would.
We still don't know between log n and 2 log n. We still don't.
Okay, that's a different thing. So you could ask, in such a graph, can I find a clique of size between 1 log n and 2 log n? And that's different. That's like not a hypothesis testing question. That's the search version of the question. Okay, so often you think like if hypothesis testing is hard, then search is hard, and that's true. But in the regime between 1 log n and 2 log n, hypothesis testing is impossible, but it might still be the search problem is hard. Okay, if you didn't follow that last part, don't worry about it. Okay, so planted clique is one example. Let me see how we can formulate another problem. So let's look at learning parity with noise. Let's say this is the sparse version. So I claim that I can also cast learning parity with noise in the same framework. Like here what I want to do is I want Q to be a distribution which has a matrix A and just random vector. Okay, let's call this Y. I don't want to do X because I already have X here. And Y would be IID 0, 1. A lives in R M by N. Y lives in 0, 1 to the M. Okay, so here my distribution is a joint distribution over matrices and the vectors are random. Now, if I want to have sparse learning parity with noise, I can't exactly necessarily take the entries of A to B product, like a distribution over the entries of A to B product, but I can do all kinds of things like say well, A is going to be represented by, so each row of A is a subset S of the variables N of size, let's say K. So what I can do, and I want to have M different rows. So what I can do is I can include each subset of N of size K as a row of A independently with probability M over N choose K. Right? This is just a simple way to take this problem, which I wasn't thinking about as a product measure, and turn it into a product measure. So now I'm just including every possible row that I could have included with probability M over N choose K independently, and in expectation I'm going to get M rows, so then I can basically get learning parity with noise like this. In this.
Is that a real matrix?
Yeah, why did you put R? Yeah.
A is over 0, 1 also?
Oh, sorry. I just put R here because
So you're over 0, 1.
it's technically correct, but this is more correct. Yeah. Okay, and so this would be the null distribution. This whole thing was just saying that I could make it a product distribution if I wanted to. And then my planted distribution would be that instead of having Y, I'm revealing X plus E, okay, where X is the planted solution, and E is a vector of IID noise, say.
With some parameter? I mean, like, some parameter doesn't have.
Yeah, with some parameter, like. Okay, so okay, these are two problems which are hopefully familiar. There are many problems which are probably less familiar to you all that fall in this framework, but that people in statistics have studied. Oh yeah, sorry, I missed your question.
Is the hardness of the planted clique testing somewhat the same as the average case hardness of clique?
No, planted clique is much easier. Okay, it depends on how you're measuring hardness exactly, but planted clique is easier than clique. So,
But average case.
oh, you're asking if there's a worst case to average case reduction, or?
I mean, it is still easier than the average case version of the clique problem, of the decision version of the clique.
So okay, so first let me say that in this case, I don't for clique I don't know of a worst case to average case reduction, and I think if there was one, it would look pretty weird. And one thing that I'll say about so if you're looking at this average case version of clique, one thing that we know is that we know that the size of the maximum clique concentrates extremely well. Like the size of the maximum clique is going to be 2 log n plus a term which is like little o. Or it's of order log n, and maybe it's like subtracted, and then I mean we know like what the terms are going to look like out, a couple terms, and so that asking the decision version, like does there exist a clique of a certain size, is not so interesting for average case clique. The search version of the problem, there is some regime in which it's possibly hard, but it's not so clear, I think.
Thank you.
Yeah. Yeah, good question. Yeah, let me tell you one problem that has a little bit more of a statistics-y flavor, which is in this planted versus null kind of. Oh yes, it's Shafi.
The
Yeah.
search version in the planted click is find the click or say doesn't exist. Yes. Given
Yeah.
given a
Given a number k. Yeah.
you are asked does there exist a click of size k or not?
Yeah. The decision version of the problem is given a graph G and a target integer k. Does there exist a clique of size k?
And the search is to find it, or
And the search is to find it or say no.
and the distinguishability, which you usually think about, is to distinguish, and you're saying that's pointless.
It's pointless if k is tiny.
If k is small enough, then it's pointless. If k is less than this lower bound, it's pointless. Yeah. If k is bigger than this bound, and you know that you have a sample from Q, you would always say no, because you're right with probability 1 minus level O1.
I think that the planted click sounds like a natural formalization of what you would think of if you wanted to do an average case question of click, right?
Yes.
It's not question of click. Because what will be the two distributions, right? So this is a natural.
Yeah, it's totally natural. I guess the history of planted clique is maybe okay. I'm like really I didn't prepare this part of the talk, so, but I believe that what happened is that Dick Karp in maybe like '76 suggested let's look at clique in random graphs. Here he noticed that even though it's true that the maximum clique has size 2 log n with really high probability, he only knew how to find one of size 1 times log n. That's still where we're stuck today. But then later on, people, I believe like maybe Mark Jerram is the first person to have suggested this, to say, well, let's look at this hypothesis testing question instead, where we're, instead of trying to find the largest clique, we're trying to see, can we tell whether there is a larger clique here? And then here the problem appears harder. Like instead of a 1 versus 2, like instead of a factor 2 gap, there's a factor root n gap.
I think it's not only an average case problem, but also a gap problem.
Yeah. So this would be a gap problem. Because otherwise, so the gap problem is easy, right? Because of the concentration.
Yeah, but this is how you define it to be not trivial.
Exactly. Yeah.
Okay, let me tell you one more example. I just want you guys to feel like this is actually like you've seen the familiar, now let's see something a little bit more exotic. Okay, so this is a problem that I'm going to call tensor principal components analysis. Okay, and in the case of the null distribution, what I'm going to see is I'm going to see a tensor T living in R n by n by n. Here I really do mean R. This was I have to pick this, and the entries of T are just going to be sampled independently, normal 0, 1. Okay, if I want, I can make it symmetric so that this is like the same value for any permutation of I, j, and k. But ignore this detail for now. So on the one hand, I have just like a 3D array of just IID normal entries. In my planted distribution, what I'm going to do is I'm going to pick T to be equal to a rank 1 tensor. So V is a unit vector. Lambda is a scalar. It's some kind of signal-to-noise ratio. It's controlling how big the norm of this rank 1 tensor is. This is rank 1 tensor. And then I'm going to add to it a matrix, or a tensor of normal 0, 1s. Okay, so here what I've done is I've taken a totally random tensor, a Gaussian tensor, and I've added to it a rank 1 spike. Okay. Now, like this is like a tensor version of a spiked eigenvalue problem, right? Like if these were matrices, here I would have started with a random matrix, and here I would have added to it a rank 1 matrix. And if my weight on the rank 1 matrix is large enough, then I expect that the spectrum of my planted matrix starts to resemble this rank 1 matrix that I planted. There's tensor versions of the same problem, and it's well motivated in statistics because you're interested sometimes in exploring correlations in higher dimensional arrays of data, right? Instead of having like a pairwise correlation, you want to understand 3-wise correlations.
Sorry,
Yeah.
I don't understand. So on top, everything is normal 0, 1.
Yes.
On bottom, everything is normal 0, 1, but you add something to it.
Yeah. So if you wanted, you could say like the first step is you sample some unit vector v. This is going to be your planted hidden thing.
Okay.
And then in your second step, you're going to sample Tijk to be normal, but the mean will depend on the entry ij and k. The mean is going to be lambda vi times vj times vk, and you're still going to have variance 1 noise.
Yeah, but why is that hard to distinguish? It depends how.
It depends on lambda.
Yeah.
It depends on lambda. Okay, so I'll tell you what we know. So basically,
Sorry, in step
Yeah.
2, the noise is also independent between the
yes. So these are independent samples. They're not, the entries aren't identically distributed because the mean depends on the index. And the question is, when is this easy and when is this hard? That will depend on lambda. Like, if lambda is 0, then there's obviously no difference between these. Okay, so it turns out that if lambda is bigger than root n, the problem is information theoretically solvable. Below, they're actually the same. The distributions are the same. And when lambda is less than n to the 3/4, we believe that it's hard. So here it's easy. In this intermediate regime, it's probably, well, it's hard as far as we know.
In V is
We
just
don't know any polynomials.
0, 1 is like a uniform beat or a uniform unit
Yeah.
vector.
So you have some freedom how you choose V. It seems like it doesn't help you. I mean, if V is very, very sparse, then we can talk. But if V is like either you can pick it to be a sign vector or you can pick it to be a random vector on the sphere, it won't matter. Like, it won't shift these thresholds more than qualitatively the thresholds are the same.
What's the complexity of the best known algorithm? Is it quasi-polynomial or higher?
So in the regime between n to the 3/4 and root n, the best known algorithm interpolates sub-exponentially. So like if you're at like if I write here, can you still see? If you're at lambda is n to the half plus epsilon, then the running okay, let's see, n epsilon over 4, I think, then the runtime is 2 to the n to the 1 minus epsilon. Yeah. So you have sub-exponential security as you interpolate between these ranges.
And is there a meaningful finite field version of that?
Is there a meaningful finite field version of this? I think we could probably formulate one, but I would have to think about it. Yeah. Okay, so yeah, question.
Why rank 3 tensors? What's special about 3?
Why? Okay, I guess that like rank, I'm thinking. I guess order 3 is like how I would want to call it, but rank is fine. So there's nothing special. Nothing special about 3. The 2 is kind of special. 2 is a matrix, and 2 is special because we have spectral algorithms at 2.
So that's easy.
So that's easy. 2 is easy, but 3 and above is hard. And so here 3 was just because I wanted to be able to write down all the indices concretely. But you could have the K tensor version of this, and there would be a different hard regime here.
What is the best algorithm?
What's the best algorithm? So there's an algorithm based on sum of squares in this regime. Like I guess okay. So me and my advisors in 2017. And also in parallel, Buddy Prolo, Guruswamy, and Lee, also in 2017, came up with an SOS algorithm that works in this regime. But actually, you can also get a spectral algorithm running in sub-exponential time that matches this. And I think that maybe one of the Kikuchi papers does that. I'm sorry, I don't remember the citation off the top of my head.
Okay, so so we understand the definition.
Yeah.
Unit vector here means that the norm is 1.
Yeah.
Okay. Why did people look at this problem?
Why are people looking at this problem? Yes. So okay. So the reason that this if you're thinking about doing statistical analysis on an array of data, this is a natural question. Like, say that I have a 2-dimensional array of data. One of the main tools in our toolbox is singular value decomposition or singular vector decomposition. If you want to know what are the interesting correlations in a 2D array of data, you compute the top left and right singular vectors, and you say, okay, this is the interesting direction of correlation, right? Now for tensors, you could say the same thing. Like you have a 3D array of data. I want to know what is the best like one-dimensional tensor or rank 1 tensor that describes this data set. But unlike SVD, for tensors we don't have algorithmic SVD. It's an NP-hard problem to compute the tensor singular vector decomposition. It's even like a question like, what does this mean? But let's not get into that. But now what you could say is you could say, okay, well, the worst case version is hard, but what if I formulate a natural average case version, right? Like maybe the reason why it's hard is because a typical worst case tensor has no obvious direction of correlations. Yeah.
Are you saying that if you sample from P, then it's an easy problem?
No.
It's value decomposition?
No, it depends on what lambda is.
What?
But when lambda is bigger than n to the 3/4, it is an easy problem.
Huh.
So like like suppose, okay.
I'll tell you why I'm asking.
Okay.
There's this paper by Zamil and Vinod, this new paper, and I think that Baverman has some analogous, where they come up with some matrix where it looks pseudo-random based on some version of, I guess, WE or whatever. But the merit of it is that you can do matrix multiplication there easily in linear time rather than. So there's a reason why the assumption that they introduce is interesting, because it produces these new matrices which are distinguished from random where you can do something efficient. So I'm asking whether there's something here. Okay, one thing is whether Q and P are different, and you can research it, and it's very interesting. But I'm curious, why P? Is there something about P that computationally is interesting that we can do with it?
Not as far as I know yet. So this P is like this P, it's more like motivated by a question of like, what is the minimum structure that you need to, like, what is the simplest statistical model that you can have of a tensor, which is random but has an interesting rank 1 correlation in it. That's the motivation for P. But if you want to start using, if you want to, like a
this correlation quickly, you can.
Not necessarily. It depends on whether we're in the easy or the hard regime. But I think that if you're a cryptographer, it is natural to want to say, okay, this P isn't structured enough. Can we have a different P which is more structured and will let me do something with it? And this is I think like a really great question, and I want you all to think about it.
It's some kind of a low complexity pseudo-random generator over the rails, right?
Right. Okay. Okay, excellent. So these are some examples of our hypothesis testing setup. I will now erase some of them. Like, perhaps I'll begin here.
Is this a pseudo-random channel? Yeah, you still need a normal distribution.
Yeah, but I think it's less than. And like against that more than against that we add noise in that.
So, okay, now what I'm going to do is I'm going to introduce a model of computation in which I'm going to be able to rule out attacks on hypothesis testing models, or on hypothesis testing questions. And the model of computation is going to be extremely simple. So basically what I'm going to ask is I'm going to ask that I have a polynomial f of x. Okay, so really, like, here we're thinking of a sequence of polynomials, f, like 1 for every n, or something like that. And I'm going to ask that the difference in the expectation of f under p versus q is really large compared to the standard deviations. So the square root of the maximum of the variance under p of f and the variance under q of f. Okay. So my model of computation is that I'm allowed to, I observe x, I'm allowed to compute a polynomial function of f, and my goal is that the difference in the expectation of f under the planted versus null distributions exceeds the standard deviation in both. Why do I want this? I want this because then I can analyze a threshold function applied to f using Chebyshev's inequality. right?
Maximum of the two variance.
Yeah. So okay, so what is the algorithm, right? So here I have, let's say that without loss of generality, my expectation under null is 0. I can always achieve this by shifting, right? So what I'm going to do is I'm going to threshold f. I'm going to say if it's at least half of the value of the expectation under p, then I'll say I'm in the planted case. Otherwise, I say I'm in the null case, okay? And now I know that it's very unlikely, because I have a bound on the variance, that I'm actually in the null. I mean, I'm actually in the null case or in the planted case, right? So this is the idea for how the algorithm works. Now you could say, okay, and to make it like more interesting, I mean, I want a restricted model of computation, really. So here I'm usually interested in thinking about a degree d, where d is a function of n polynomial. And I'm going to restrict the degree of this polynomial. Otherwise, I guess I could probably do anything. It's not a very interesting model of computation. Okay, and here, like we've forced ourselves to do our analysis of the ability of this polynomial to distinguish using Chebyshev's inequality, which is kind of a weird thing to do, maybe. I mean, it's the simplest analysis you could want to do, but it is a restriction. Okay. So okay, why? Like, what kind of algorithms are actually like this? Like, what does this capture? Well, okay, so let's look at the example for planted clique, okay? So what's the simplest algorithm that you could try to solve planted clique with? You could do like an average degree computation or like a maximum degree computation. Both of these are capturable as a polynomial, a low degree polynomial algorithm, right? The average degree, or the average degree is just you're counting the number of edges in the graph, basically. That's like a degree 1 polynomial in X. The maximum degree is like a logarithmic degree polynomial in X, because you're just taking the sum of the log nth powers of the degrees of the individual vertices, and you can show that this somehow captures the max. So this easily captures kind of subgraph counting. Okay, it also captures spectral algorithms. The reason why is because if I want to know what is the largest eigenvalue of A, of a matrix A, I can get it by looking at the trace of A to the log nth power. If I take, this is approximately going to be the maximum eigenvalue to the log n, as long as I have logarithmic power in n here, right? So, and if I think about A as my input, then this is a logarithmic degree polynomial in my input. So these are two kind of natural class of algorithms for hypothesis testing, which are captured by low degree polynomials. Okay, I'll say a little bit more on this later, but it still doesn't like really motivate why I would do this. The real reason to do this is because once I restrict this to be my model of computation, I can very easily get lower bounds. Okay, so I can really easily rule out attacks in this model of computation. This is the low degree heuristic. Okay, so I have the low degree method. Let me write down an optimization problem. I want to maximize over polynomials of degree at most d the difference between the expectation of the polynomial under the planted distribution and the null distribution, subject to controlling the variance only under the null distribution. Let's say that this is equal to 1. Okay, so if the value of this program is little o of 1, I cannot solve the P versus Q testing problem in the degree D polynomial computation model.
So you mean if the max of this difference is the log one?
Yeah, so here I'm choosing the best polynomial of degree at most D. If I have the case that the value of this program, which is the maximum difference between expectations under P and Q, of all polynomials with variance 1 or less under Q is little o1, then I can't solve the problem better than random guessing. I can't solve this hypothesis testing problem better than random guessing. Why? It's because here I would have the opposite of this being true. I mean, what I'm doing is I'm dropping the constraint of being bigger than the variance in the planted case. I'm saying let's only care about the variance in the null case, right? And even if I only cared about the variance in the null case, this is not achievable. The best polynomial of degree D has that this is less than this by a lot. And so,
the point about the difference between communities, here the notion of indistinguishability refers to a vanishing advantage, whereas in cryptography we usually want it to be better than any inverse polynomial, what we call negligible. So here little o1 is really...
Well, right, you could, if you wanted to, if you care about the degree of advantage, here you could introduce some quantitative measure, right? So if you could say if this is epsilon n, then you can't test better than half plus. Okay, now here this would be some delta of n, which it's probably like the square or something, but I can't do the Chebyshev in my head.
For the first and third examples, we actually do have inverse poly
Yes.
in distinguish.
Yes. Yes, for the first and third example,
In the other gene, like in the planted click, 1 over square root n advantage is trivial by counting. What the distinguisher Tselil mentioned, and I guess similar for the PCA.
Right. It depends where you are in the hard regime, but you can actually get epsilon n going to 0, like I guess sub-exponentially fast in tensor PCA, say.
In tensor PCA,
yeah.
Unlike click.
Unlike click, yeah. Right. It's problem dependent. Like I mean, this quantity is problem dependent. I'm gonna use the notation. So you guys know the chi-square distance? It's a statistical distance. If you don't know it, don't worry about it. But this is some kind of natural low-degree version of the chi-squared divergence between the planted and null distributions. So this is the notation that I'm going to use for it. Okay. So the nice thing about this is that this quantity is often computable. Like it's very analytically tractable. So let's see, maybe I'll erase the model of computation.
What's the relation between epsilon and delta in the previous?
I think delta is probably square root of epsilon, but don't like, you know. I'm trying to do the math in my head, so there's a pretty good chance that I took a square root. I should have done a square, but I think it's the square root. Okay, so the good news is that this is so this has a closed form solution. Okay, and in particular, if there's a natural basis of orthogonal polynomials for Q, right? Then so if H alpha is a basis of degree D polynomials, which are orthonormal with respect to the inner product defined by Q. So like the inner product AB defined Q is just the expectation of A x bx for x sampled from Q. then the closed form is just that I just have to compute the sum of the squares of the expectations under P of these polynomials H alpha. Okay, like, and this is a little bit abstract, but like concretely, if Q is, say, Bernoulli half to the n, then the H alpha are just the degree D Fourier characters. So it's just the monomials. Okay, so in order to understand what is the value of this optimization problem, all I have to do is I just need to compute the expectations of all low degree Fourier characters under the Planta distribution, which doesn't sound that hard, right? It's like for example, if I have dy's independence, I know that this is just going to be 0. If I have dy's independence under the Planta distribution, I know that I just get 0 here, and then I automatically get that this is small, and then I get a lower bound for degree D polynomial hypothesis test. Okay, so this is great news. Like, so checking if my low degree chi-square divergence is little o1 is often like pretty easy. By pretty easy, I mean, you know, it's an annoying calculation, but you can sit down in an afternoon and you can do it. I mean, or you can sit down in a couple of afternoons and you can do it. But it's not like totally daunting, because at least we have some way to turn a crank and get some kind of lower bound against a restricted model of computation.
Polynomial in time n to the power of the n is d, right?
Polynomial, like you mean the amount of time that it takes me to do the calculation of this polynomial?
No, I mean the time you spend will be.
Oh, okay.
Time.
Yeah.
Right. Okay, yeah, this is
Test.
the test. Yeah. Okay, this is the thing I should have said before. Like, right. So evaluating f of degree D takes time at most n to the D, order n to the D. Right, because there's only n to the D monomials, and I just have to evaluate them all and sum them up.
So basically, consider D up to log or polylog. What is the typical highest D that is considered interesting here?
I will answer this question in 1 second. Do you have a question?
Yeah, so here, because probably that's what you meant, because you gave the example with the Bernoulli Q, but in general, like, it can be hard to find these polynomials, the H alpha polynomials.
Yeah. Remember when I said that I wanted my null distribution to be a product distribution? In this case, it's usually pretty easy to find out what the polynomials are. So say if I have that Q is Gaussian, then these are the Hermite polynomials. And if I have that Q is Bernoulli's with different probabilities, then I have to work with the like Bernoulli P Fourier characters. But as long as you have product measure, then it's not so hard, I think, to do this.
But the framework will be more general. It's just that I'm stuck with the hard.
Yes. Okay. So the heuristic is as follows. Okay, so actually, like, what have we concretely done? So concretely, / provably, if we know that this low degree chi-squared is O of 1, then testing P versus Q cannot be done in the model of computation, which is that you have to take degree D polynomials and analyze them with Chebyshev's inequality. Okay, now this might be a weak model of computation. This doesn't capture like algebraic attacks. Such as Gaussian elimination. Or lattice methods. Okay, but it does capture, as I was mentioning before, it captures subgraph counting, and it captures spectral algorithms if you allow D to be logarithmic in n. And for this reason, usually we like to think of logarithmic in n as being the first kind of like legit value at which you think that this is a non-trivial guarantee. And we think, okay, so these are two things that we have. We also know that if the low degree chi-squared divergence is small, then statistical query algorithms don't work. Okay, so this is based on a paper that I wrote with Matt Brennan and Guy Bressler and Sam Hopkins and Jerry Lee back in 2021. So if we can prove a lower bound in this model of computation, then we get a lower bound in a slightly different model of computation. To tell you the details of this statement would take a long time, so just like take it for granted. Like I'm happy to tell you more later. And it's also suspected, although like the formal statement again would have to be pretty nuanced, is that this probably implies some SOS lower bounds. There's this really influential paper by Boaz Barak and Sam Hopkins and Pravesh Kothari, John Kellner, Ankar Moitra, and Aaron Patechin from 2016, where they basically, effectively what they do is they kind of use the fact that this happens in order to prove a lower bound for planted clique. And that's actually kind of where the idea to propose this criterion even came from. It kind of came from their paper. Like they sort of set forth a proposal for if this happens, then you can prove a degree something like D SOS lower bound for hypothesis testing. But we don't know that this is generally the case, even though it has been, like the strategy has been executed for a number of other planted problems, like tensor PCA, for example. So you'd be there's this hypothesis that Sam Hopkins wrote down in his thesis, but it's kind of implicit in some of these prior works, including here. So here's the hypothesis. It kind of goes as follows. So Sam hypothesizes that if P versus Q satisfies some conditions. Okay, I'm going to fill in what they are later. And the low degree chi-square divergence is vanishing when D is at least log n. Then no polynomial time algorithm can test P, like a Q, versus a noisy version of P. Okay, so if I know that the low degree chi-square divergence is small, at degree at least logarithmic in n, then I shouldn't be able to tell apart null sample from a sample from the planted distribution, but I have to add a little bit of noise here in order to make this valid. Okay, so
now there's no Because on the degree, it's not a polynomial.
Okay, yeah, so, okay, great. So actually, like, now you could get a little bit nerdier. You could be like, oh, there's no n to the d over log n time algorithm. But this version was actually very recently refuted in a paper of Buhai, Shea, Jane, and Kothari. So
Which version was refuted?
okay, so this
over log n.
yeah, this regime is not refuted. Here you could have a priori said maybe it should take time n to the d over log n, but this is refuted as of like a couple months ago. But the polynomial time version is still not refuted. I didn't tell you what the conditions are. Here they're like pretty important. Okay, so let me say like one at a time why we need these conditions. So here you could have said, well, why can't you give me a guarantee of Q versus P? Why do you have to do this noisy part? The reason is because of basically Gaussian elimination, right? So one dirty secret, well, it's not really a secret, but one thing that I didn't tell you yet about this low degree chi-squared is that it actually can't tell learning with errors with noise rate 0 apart from learning with errors with noise rate like 1/3, okay? So it will give you the same prediction regardless. It's not sensitive to the amount of noise that you add. And okay, I agree it's a little bit embarrassing, but that's why we say, okay, let's just add noise in post so that the predictions are accurate. Okay, another thing is that even if you add this noise, you could worry that there's some kind of error correcting code or something where you can still tell that it's a code even if you've added noise. So the condition that you want to have here is you want to have a condition where P is permutation symmetric. And the notion of permutation symmetry, it depends a little bit on the specific problem that you're considering. But generally speaking, you want something that's invariant to permutations. This refutation of the n to the d over log n time occurred because of using a permutation symmetric error correcting code. But still, it takes quasi-polynomial time to do the inversion of the permutation. Okay, and then the second thing is that I think if you're not in the situation where Q is a product measure, then I actually don't know to tell you what noise to take here, and then things are a little bit weird. But I think if you have these two conditions, then this is still a reasonable hypothesis. Yes. Okay, perhaps, let's see, it's pretty, okay. We only have 5 minutes left. Maybe the right thing to do is to pause for questions, because if I just press on, but there are questions, then it's a bad idea. Other questions? Yeah.
Can we do this kind of hypothesizing algorithms, like some classical version of EFI pairs?
Sorry, what are you saying?
Is this some kind of a classical version of the EFI pair, which is, you have two distributions that are statistically close, but statistically par, but computation is distinct?
Yes,
This is exactly a framework for deciding if a problem has this property. So this is a heuristic, like this is saying.
So if we assume something like this is hard, this is possible to build some cryptography, just like we do in quantum.
Yeah, I think that would be. I mean, like that's my hope for what you'll do.
Wait, what's your hope? Sorry, I missed the.
My hope is that, okay, so suppose now that you are all cryptographers, okay, and you want to design a crypto system whose security is based on not being able to tell apart some distribution P from some distribution Q. Yeah. And say that it satisfies these conditions. Okay, now I promised you that computing this is probably not so hard, okay? So I want you to say, okay, let's check if this is a plausible average case hard problem, average case hard testing problem by calculating this, checking that it's little o1. And then if it is, then we know that at least we resist a bunch of different types of attacks, but we're not necessarily capturing every attack. There's algebraic methods and stuff that we have to worry about still. Yeah, and some people have already started doing this, like Yuval and co-authors have been kind of doing a little bit of this. So right, so yeah, so like the applications to crypto, right? So if you have a crypto system whose security is based on the assumption that P versus Q is hard, you can check if it resists these like low degree attacks by computing this chi-squared distance. Okay, this is kind of what I hoped to say, and in particular, like the tensor PCA example shows you that there are problems that are like kind of exotic and pretty different, I think, than what people are using in cryptography that do appear to be hard in this way. Here you could be a little bit concerned about this polynomial time versus d over log n thing, but I maintain that the example that was used to refute this was an example with some pretty special algebraic structure. For a problem like tensor PCA, when there's almost no structure in the Planta distribution, I think it's very unlikely. I mean, I still believe this stronger prediction of the low degree heuristic. Okay, at the very least, a different thing you could say is you could say that at least you can rule out a certain class of attacks, which perhaps that you can rule out before. Yeah, question.
But going back to the concrete parameters,
yeah.
Said that I missed it, but like, is there something specific about being close to log n, or can I expect to be able to prove something similar for a much higher d, just to be safe, so if I want to make a concrete assumption?
Yeah, okay, so you can definitely prove stuff for, the special thing about d is log n is that if you're not above log n, then you didn't rule out spectral algorithms. So if it's below log n, then it's super suspicious. The larger the d, the stronger a thing you've proven, because you've captured a larger class of attacks, like higher degree attacks. But the question is, what does that mean for the running time of the algorithms? Okay, and previously it was plausible that the runtime of the algorithm would be at least n to the d over log n, but now this specific bound is refuted. So there's a paper by Buhai, Shea, Jain, and Kothari from this year, where basically they show that there are problems where you can take d to be n to the 1 over 100, say, but the running time is quasi-poly. But these problems are some kind of exotic problems. Like they're based on error-correcting codes. Like they're based on some permutation-resistant error-correcting codes. And I don't think that the typical hypothesis testing problem that you would consider has this issue, and so this might still be a plausible lower bound. But I'm certainly not gonna bet my life on it at this point. Yeah. Yeah.
So my question is purely from a consumer perspective.
Great.
Say that I'm a cryptographer and I want to propose some new assumptions and I want to cryptanalyze it.
Yeah.
And this seems to be a generic paradigm for me to cryptanalyze it. And the first thing is we usually work over finite fields. Are there anything I need to be aware or pay attention to if it's finite field?
I think over finite fields, things can be extended pretty naturally. The one thing that's more annoying over finite fields is that computing this quantity, I mean, it's still possible, but I just don't, like, if you asked me to do it, it would take me a long time because I would have to be like, oh, what is the correct basis for orthogonal polynomials for the finite field? You know, I'd have to get used to doing the computation, but I don't think that there should be a problem.
Still have Fourier basis in.
Yeah, exactly. I just don't know. I mean, I just can't. Like, I don't remember how how it works. But there's no.
It's a Fourier basis, and the equation that you use to compute the holds, right?
Yeah, definitely, yeah.
So let's think about something very concrete. Let's say I want to propose LPN is hard for very special noise distribution.
Yeah.
So the Q stays the same, P slightly change. Now, if I say I analyzed according to this hypothesis, my noise distribution is kosher, do we feel this is a good way of proposing this new assumption?
Right. So the thing that I mentioned a moment ago is that actually the noise, like this method does not seem to care what the noise level is for LPN, because when you have really low noise, you've already eliminated Gaussian elimination, but the problem is that you can look at, like, you can brute force search over subsets and that kind of thing, right? So somehow this doesn't seem to capture the trade-off in the noise rate for LPN very well, and I agree it's very sad that that's not the case,
So I
especially for us, yeah.
I see.
Not for LPN. I think you can use it as a sanity check that it's not broken, but you can't use it really as an indication.
Yeah.
Because our work does use algebra. Like we're very, at least many of our assumptions are algebraic, and in that regime, it seems like it's not necessarily.
Yeah, it won't help you at all with algebraic things. But the kind of thing that it has been useful for is to say, like, that planted subgraphs, which aren't cliques but other kinds of cliques, are hard to find. Like Uvad has at least one paper where this is the kind of underlying assumption, and then you can do things like plant trapdoors that are, you know, like based on the hardness of finding a certain subgraph or subhypergraph in some graph, which is publicly available. Like you think about the matrix A as defining a hypergraph, and you think about your trapdoor as being some specific subhypergraph, and the adversary can't find it. For that, I think this is a pretty legitimate thing, because I don't think algebraic tools could help you very much. But it doesn't seem, it's very, very ignorant of algebraic attacks and that kind of thing. So I don't think it's good for LPN specifically, unfortunately.
So say that I do LPN with your hypothesis plus rule out Gaussian elimination separately.
I think that's pretty good, yeah. Like it does correctly capture the trade-off of the number of equations versus the number of variables for LPN, just not the noise rate.
I guess the bigger question, I don't know if it's to you or to all of us, it's, so once let's say we believe this conjecture, so it means implicitly we get a one-way function, right?
Yes.
We're not because it's statistically far,
right.
But I guess we have a lot of one-way functions, so is there any, I mean, as I said, I'm not sure it's to you, but if you want to be like public encryption or something, is there, any idea which P and Q are more friendly towards this? Because somehow it seems hard to build like advanced crypto from this.
I agree. So I guess like there's a paper of like the paper of Applebaum, Barak, and Wigderson from 2011 is constructing PKE. And what they do is they take a combination of a linear-based encryption scheme, plus they plant a trapdoor whose security can then be verified using these kinds of tools. Let me see. I wrote down the citation. Like, so they make some assumption about they make an assumption about the security of their trapdoor, and then later it was verified in a paper of Bogdanov, Kothari, and Rosen from 2023. So I think I'm not sure if you could, I think it's a great question. Like, could we get public key encryption just based on this type of one-way function? I guess you'd have to have this pretty special P and Q, but it has like sort of been done, and I think it would be nice to see more works like these. Like, to me, it feels like the types of P and Q that you can say are hard to distinguish here, there's like a really big diversity of different problems that you could hope to show are hard in this way. And then, I'm not a cryptographer, so like my students and I, like, we sit around and we talk about it, like, oh, could we like construct public encryption? But we don't really know what we're doing. But maybe you all do, and it would be nice to see more intersection, more interaction.
Okay.
Oh yeah, you.
Can you say more specifically what does it mean to add noise to P? I mean, P can be.
Okay, yeah. So suppose that Q is like Bernoulli half, right? Then adding noise to P would be I first take a sample from P and then I resample every coordinate independently with probability 0.001. So it's just like literally adding noise to, or in the Gaussian case, it would be like I would just add a Gaussian noise to my sample.
Some fraction, P is a graph.
Oh, if P is a graph, then what you're doing is you're just resampling edges with small probability. So you just put it through a Bernoulli channel with a noise rate that's some small constant, say.
You're assuming constant noise, right? So for these quantitative things to make sense.
So like I guess that you would everything is quantitative. So but yeah, you can think about really small constant noise, or you could think about tuning the noise amount, and then you get some kind of sensitivity in these conclusions. Okay, I guess I'm pretty over time, so sorry, Rachel.